friends, welcome to NIKRA'S Expert Learning. In today's video, we are going to discuss what is fluid kinematics and methods of describing the fluid motion, and also we'll be discussing the types of fluid flows. Before starting today's topic, if you like this video, please like, share and comment to the channel, and don't forget to subscribe to my channel, guys. Coming to today's topic, fluid kinematics. It is the branch of science which deals with fluids in motion without considering the forces causing the motion. So here whatever the motion that is happening, we'll be considering that, but we'll be neglecting the forces which cause that motion. Methods of describing fluid motion. We have two methods, Lagrangian method, Eulerian method. Coming to the first one, Lagrangian method. In this method, a single fluid particle is followed during its motion and its velocity, acceleration, density, etc. are described. Here, whatever the fluid we are considering, in that we'll be considering only one material, one particle. So we will be following only that particle, we will be observing its motion and determine the characteristics such as velocity, acceleration, density and etc. Next, in the Eulerian method, the velocity, acceleration, pressure, etc. are described at a point in a flow fluid. This method is generally adopted in fluid mechanics. So here we are observing the characteristics at single point, but here we are following a path of particle in the whole fluid. Next, types of fluid flow. First comes the steady flow and unsteady flow. We'll discuss what is steady and unsteady. It is defined as the type of flow in which the fluid characteristics like velocity, pressure, density, etc. at a point do not change with respect to time. So we are mentioning that this velocity, pressure, density, whatever the characteristics we are considering, that will not change at any point, at a point considered with respect to time. That is, the velocity with respect to time, we are mentioning as 0. Whatever the change in velocity with respect to time is there, that is 0. Pressure and density. This is steady flow. As they are constant, the change is 0. Coming to the unsteady flow. It is defined as a type of flow in which the fluid characteristics like velocity, pressure, density, etc. at a point will not change with respect to time. Here, whatever the change is there, that is not equal to 0 because there is some change. Remember, here we are just seeing at a point in steady and unsteady flow. Next, we have uniform and non-uniform flow. Uniform flow, it is defined as a type of flow in which the velocity at any given time does not change with respect to space or length of a channel or pipe. In steady and unsteady flow, we are seeing a characteristic at a point with respect to time. But here, we are seeing these characteristics at any given time. At any given time with respect to space or length. Will not change, okay? That is uniform flow. So here, whatever the velocity we are mentioning with respect to the space or length is equals to 0. Where S is equals to L is equals to space is equals to length, okay? These are the characteristics. Coming to the non-uniform flow, it is defined as a type of flow in which the velocity at any given time will change with respect to space or length of the channel or pipe. Remember, in steady and unsteady flow, we are considering at a point with respect to time. But here we are seeing at any given time with respect to space or length. Okay, if it is changing, we are saying non-uniform. If it is constant, we'll say uniform flow. Next comes the laminar and turbulent flow. Okay, laminar flow. It is the type of flow in which the fluid particle move in well-defined path. The particles move in layers or laminars, gliding smoothly over the adjacent layers. See, here the flow would be in layers. This is in a well-defined path. The particles will travel in a well-defined path. Okay, and this will form a layer. Okay, whatever the layers are there, we are calling it as laminars. That is why we define this path, this flow, as laminar flow. Okay, each layer will be gliding smoothly over the adjacent layer. Next comes the turbulent layer. In this, there is no defined path over here. It will just move randomly. Okay, in a zigzag manner. It is the type of flow in which the fluid particles move in a zigzag manner. So for pipe flow, the type of flow is determined by a dimensionless number called Reynolds number, which is defined as a ratio of inertial forces to viscous forces. Inertial forces to viscous forces. Mathematically, the Reynolds number RE, it is defined as RE, okay. It is equals to inertia force to the viscous force ratio. Okay, but mathematically we have some formula for this Reynolds number. Remember, the laminar flow will have some laminars, that is layers, which will be gliding over one another, and turbulent means a zigzag manner flow. So we'll see the formula of this Reynolds number now. Reynolds number for pipe flow, we have closed conduit flow. Okay, remember, whenever it is a pipe flow or a closed conduit, okay, here the formula would be rho Vd by mu or Vd by nu. Remember, this nu is equals to mu by rho. Okay, this is just a simple transformation. This nu is equals to mu by rho, where if Re is less than 2000, we mention the flow is laminar. If it is greater than 4000, we say the flow is turbulent. But whenever it is in between 2000 to 4000, the transition or medium flow is observed in the path. Okay, whatever that is between the laminar and turbulent one. Next comes the compressible and incompressible flow. Compressible flow. It is a type of flow in which the density of fluid will change from point to point. Example, gaseous matter. Whenever the density of the fluid will change from point to point, we are saying it is compressible. See, here the density is not constant. But incompressible flow, the density of fluid is constant from point to point. Example, liquids. See, whenever you are compressing some liquid, excess liquid will flow out, but will not be reduced in its volume. But gas is reduced, as we can see in compressed natural gas. Gas can be reduced in its volume. Sorry, in density. So whenever we are, see, density is equals to mass by volume. Whenever the volume is reducing, here automatically the density would be increasing. Next comes the rotational and irrotational flow. Rotational flow. It is a type of flow in which fluid particles, while flowing, also rotates about their own axis. About their own axis, they will be rotating. See, this particle would be rotating in its own axis. The fluid particles will not rotate about their own axis while flowing. See, if it is rotating, it is rotational flow. If they are not rotating, this is irrotational flow. Next, we have one-dimensional, two-dimensional and three-dimensional flows. One-dimensional. It is a type of flow in which velocity is a function of one space coordinate and time. Here, one space coordinate and one time coordinate would be there. So, V, velocity is a function of x comma t, because only one space coordinate is there, only in one particular direction. But here, whenever I am saying two-dimensional, it will be having two space coordinates, that is in x direction and in y direction. Okay, so it is a function of x comma y and also t. It is a 2D flow. If it is in one direction, we are saying it as one dimensional flow. If x and y space coordinates are there, we have to say 2D flow. In three-dimensional flow, the velocity is a function of three space coordinates, that is x, y, z. Three coordinates would be there, and also it is a function of time. So it is 3D flow. That is it for this video, guys. In the next video, we'll see what is a rate of flow, that is discharge, and we'll also discuss some continuity equation, mass continuity equation, and also some examples regarding that. We'll be solving around 2 examples on that. So that is it for this video, guys. If you like this video, please like, share and comment to the channel, and don't forget to subscribe to my channel, guys. Thank you. I appreciate you watching this video, guys.